This is a very quick demonstration of structural sharing in Git. It's meant to accompany the deeply nested blog post introducing persistent data structures. So suppose we have a Git repository. And in that repository, we add a couple of files. We'll put the string hello in a file called A and the string world in a file called B. And I'm going to commit those with the default commit message here, initial commit. And then if I run git log, you can see I have the one commit. In fact, I'm going to add that to a watch window here. I'm going to say watch every half second in color without a terminal title. Git log in color -- decorate. And let's give them graph lines. So we have the one commit there. So now suppose that I change one of the files. Change B. So now I have a new commit. Those commits are actually represented by files in the .git directory. As you can see in .git/objects, if I were to look at the hash, for example, for this latest commit is 45A95 something or other. So if in objects, there'll be 45 as a directory and /A95 is the rest of the hash. That's where that is stored. So that file on its own is not particularly useful to you. It's kind of a Git internal, but Git gives you a nice interface to see what's actually in the commit, which is git cat file. So I can git cat file. If I say, for example, -t, that will tell me the type. The type of head is, you can see here from the decoration, that head is the main branch that I'm on right now. It's the latest commit. Then it will show me that it's a commit. And I can use -p to see what's in that commit. So inside there is this tree. There's the commit message. It knows who its parent is, who the author is, and some timestamps. So the tree represents a directory. That is the root directory of the repository. So every commit has a tree that is the root of the repo at that commit. So if I look inside of that, I can see 64483FD. I'm looking at this ID, right? The tree ID. Then it has references to these blobs. Blobs are how Git represents files. So there's a hash code for A and for B. Now, if I were to look at the previous commit, head caret, it has a different tree. And if I look at what's in that tree, then it has two blobs. So for B, it has a different hash because it's referring to a different object because B got changed. But you'll see that it's the exact same object, the same blob for A, meaning it's the same file. If I look in object/CE01 this, that's it. That's the only representation of A, of file, those contents in the repository. So the two commits are sharing that part of their structure. That's structural sharing. And in fact, it's even better than that. You can, for example, if I echo the same exact content as A, which was hello, into a file called C, let's add that one. Add C, just like A. I have the new commit. If I look in that commit, I have a new tree because there's a new state of the repository as a whole. And if I look at what's in that tree, BFF9F, then in there you'll see that C and A are actually referring to the same blob. So there's structural sharing even within the commit, which is kind of cool. In fact, you can get hash object any file. And if I say C, it's because those contents will always hash to that blob. So whether I add those contents now or later, more than once in a commit, it never gets regenerated. So there's a lot of sharing here that is how Git stores content efficiently. The insight is that from commit to commit, you're changing some files, but mostly you're not. So as long as the things that aren't changed are shared by multiple commits, because those commits all link to the same object effectively through these hash codes, you're not going to have to copy the whole repository to store two versions of the whole repository. So that's structural sharing in Git. Thanks very much.